Hello and welcome to Toddcast number 24, transitioning into another phase of organic chemistry, and that is the 3D visualization of molecules. And for this grouping, it may help if you have a model kit available, at least at first. After a while, hopefully you will no longer need it. You'll wean yourself from it. But it's sometimes useful to at least have a central carbon and then four different colored spheres attached to it. Because you really only need to consider the first atom attached to a stereocenter, as we'll learn. But I'm going to start with the basics. Might not need models right away, but if you have them, great. As with everything, when we first start learning it, terminology becomes the most important factor. So I want to start with a reminder that isomers are the compounds with the exact same molecular formula, i.e. the same atoms, but for some reason they are different in three-dimensional space. And the difference is either going to be a different connectivity of the atoms, which we looked at earlier as either structural isomers or configuration, or excuse me, constitutional isomers. And then there's also going to be one we look at here that will refer to the exact same bond. So two molecules have the same bonds, but for some reason they're different in three-dimensional space. Examples in real life that we love to compare to are your right and left hand. They each contain a pinky, a ring finger, a middle finger, an index finger, and a thumb. But they are not the same. There's a left and right handedness to them. And so those will be isomeric, I guess, body parts, for lack of a better word. They have the same components, but they are not the same in three-dimensional space. So your ability to visualize that will be paramount to do well. So isomers, mentioned constitutional or sometimes referred to as structural isomers. They have different connectivity and different IUPAC names. So these two compounds, they each have a 5-carbon chain. The difference being, if I number from left to right, they give my smallest combination number, 2, 3. Then I have the methyl on 2 and the OH on 3, which would make it 2-methyl, 3-pentanol. And the next one has the OH on 2 and the methyl on 3, making it 3-methyl, 2-pentanol. So note that they have different IUPAC names. The location, the address of the methyl and the OH, the ol, are different. Okay? There's also stereoisomers, and those are going to be broken into configurational and conformational isomers. And so when we did the barrier rotation about a carbon-carbon bond in some of the previous podcasts, we were rotating around a bond, which meant we were changing the position of the atoms. So technically, we were making isomers, same atoms, but different location in space. But those are known as conformational isomers, or we sometimes said one chair conformation versus another. There's also configurational isomers, which no matter how much you rotate them, cannot be made identical. Whereas conformational isomers are just a rotation, a twist, a bend, a contortion away from being identical to a different conformational isomer. So same connectivity, different arrangement in space. So if we look at these, the CH3 is in the same spot, and the ethyl CH2CH3 is in the same spot, but the H is in back and OH is in the plane. In this case, OH is in back, H is in the plane. No matter how you rotate one, it will not line up with the other. Okay, so that's our starting point at this point. These can be broken into what's known as optical isomers, and that is because they interact with light differently. So optical isomers will have different stereocenters. So this carbon right here has an H and an OH. This has an H and OH, but in one case, OH is in front. In the case, OH is in back. And then this chlorine is in back on one, and it is in front on the other. So they will interact with light differently. So because you have a greater electron density behind the plane and in front of the plane, as opposed to in front and behind, when light comes in, it will bend differently or rotate differently, interacting with one versus the other. And we'll go into that later, but it's basically plane polarized light. It will interact with a magnetic field associated with a molecule. And because of asymmetric distribution of moving electrons, optical isomers have asymmetric magnetic fields, and so the light gets impacted by that. Geometrical isomers are another class of stereoisomers. Now, they will not have what we just described. I described as a chiral center or stereo center, a carbon with 4 different substituents and an asymmetric magnetic field as a result. They will deal with rings and pi bonds. And so I'm going to start with pi bonds, and we'll go into more detail as we go. but the ethyl and the methyl are far across from each other, and because this double bond is rigid, you can't rotate around it without breaking the pi bond. They're always across from one another and referred to as trans. Here, the methyl and the ethyl are on the same side, referred to as cis. So these have their atoms in different positions in space, but they're the exact same collection of atoms. Okay, so reminder of what isomers are. Have to know these definitions. And unfortunately, I'm going to keep on changing words on you. So structural and constitutional, I'm going to use interchangeably. Stereoisomers, I'm going to have subgroups of, configurational isomers, where they are different arrangement like these, and conformational isomers, which are just rotated differently. Okay. So stereoisomers, again, two flavors, geometrical isomers. Those are ones that are positionally fixed because of some rigid component, a ring or a pi bond. So in this case, notice the 5-member ring, cyclopentane, with 2 methyls. So 1,3-dimethyl, 1,3-dimethyl. They're not the same because this one's coming out and this one's coming out, but the one on the right is coming out in one and going back in the other. These are both up relative to the plane. This is up and that's down. So up, up, and up, down are a little different. So we'll call this cis. They're on the same side. We'll call this trans because the opposite side. Same with the double bond. This one I've added a little more confusion to it. So bulkiest group here and bulkiest group here on the same side. They're cis, but we use an IUPAC designation of Z. So when they're on the same side, they're Zis. So cis or Z. Whereas the largest group on the first carbon is now above, and this one's below, so they are opposite side. So trans is ED, ET, E when it's trans. Okay, it ends up, this one will also rotate plane polarized light, whereas these will not. So this one, although I put it in geometric isomers, which is fine because it is within this constraint, it is also these are geometrical isomers, meaning they will interact with light differently. So optoisomers rotate plane polarized light in different manners. So when I say rotate but in opposite directions, that's specifically something we're going to call enantiomers, where if one bends it right, if I switch all the groups to the opposite side, then I'll bend it to the left, so to speak, or clockwise versus counterclockwise. So these two that I placed up there earlier, they are mirror images of one another. So these are what's known as enantiomers. So if this one rotates light clockwise by a certain amount, this will rotate it counterclockwise by the same magnitude. So we'll get more into this as we go, but they cannot be superimposed. Okay, so we have our definitions. Absolutely imperative we get that to start. So see what you recognize. We typically use an asterisk to recognize a chiral carbon, and the simple and easy approach, although not technically the definition, but it's one that we often use in OChem for quick reference. A carbon with 4 unique substituents is said to be chiral. So if I look at this compound, note that there is also an H in here. So I'm going to draw an H, which wasn't there in the natural drawing. We just don't draw H's, but on this central carbon right here, there are now 4 unique substituents: chlorine, bromine, H, and methyl. So that one gets a chiral center. This one is hard to see drawn out like this, but I'm going to go ahead and make that my carbon. That's an H, a Br, CH3, and a CH2, CH3, which means 4 unique things. It is chiral. This compound, this one, when it's sp2, cannot be a chiral carbon. So we're not going to call it, or it's not a stereocenter, 4 unique things, so it's not a chiral carbon. So it can have geometrical isomers, but it cannot have chirality. And finally, the last one, CH2, 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 CH2. So those are out. sp2, so it's out. But this carbon right here has one side of the ring, other side of the ring, this aldehyde group and this OH. But if you'll notice, this side of the ring, so 1, 2, 3 to get to that point, 1, 2, 3 to get to that point, loops around. This has a mirror plane. The 2 sides of the ring are equal. So there is 1 unique thing, 2 unique things, but only 3. So no chiral center. Okay, so we're on to something here. So it must be 4 unique things, but This is one group that is symmetric. Now note that if it had something coming off like an OH, then one half is different than the other, and it would become a Carl center. So those are sometimes interesting molecules to interact with. So we're done. This one went quick. Hopefully these are well, relatively helpful information, and it'll set the groundwork, but make sure you can recognize when a carbon has four unique substituents. So thank you for joining, and I'll see you at the next Toddcast. Until then, bye.